All right. Let's just wait just a minute for everybody to settle. Um, a couple things, housekeeping. We will take questions towards the end of the webinar. So we have some time allotted for that. We should, if you have any questions, please message any of the hosts or co-hosts, and we will relay your question to the group at the end. And then we will also allow people to raise their hands and ask questions directly. So if you prefer that, we can do that as well. And with that, um, Jacob, please, with the introduction.
Hello, everybody. Good morning, good afternoon, good evening, depending on where you are. It's my pleasure to introduce Professor Burak Ülgüt from Bilkent University in Turkey. Burak has been at Bilkent since 2015. Prior to that, he got his PhD at with Hector Brunia at um, Cornell University. He did a short postdoc at Cambridge after that, and he actually worked here at Gamry for a couple of years before moving back to Turkey. And again, he's been at Bilkent since 2015. He has won numerous awards, including a couple for teaching. Most recently, the Distinguished Teacher Award for the university there. And he has been driving electrochemical testing for batteries using impedance and noise for quite a while, and working with several other professors and collaborations on doing this work. Uh, I'm looking very much forward to what he has to say here this morning, and thank you all for attending. And Burak, take it away.
Thank you very much for the intro, Jacob, and let me thank the whole Gamry team and Jerome for inviting me and having me do this. It's a pleasure. And to all the attendees, thank you very much for sparing the time from your morning or your afternoon or your evening to join us today. Okay, now Jacob did the intro, so I'm just gonna show this here. Just quickly, my story started at Bilkent as an undergraduate, and I'm right now at Bilkent as a professor. I also did a little stint at a car battery, at a lead-acid battery manufacturer when I returned to Turkey, but that only lasted a year for a number of reasons. Okay, so without further ado, let's get right to it. Now, as my title suggests, my talk will be done in two separate acts. I will be talking about impedance and noise, both geared for battery analyses. Okay. Now, I like talking about, whenever I talk about impedance spectroscopy, I like starting with this slide. Now, whenever somebody wants to mention how important their field is, they always plot the number of publications per year. I hate those plots because the total number of publications is also growing, and I never know how to normalize it. So whenever I'm plotting data that I don't trust, I like using this XKCD style of plotting. For those of you who are familiar with the comic strip, for those of you who are not, I highly recommend it. So the rise of the number of publications is probably due to the overall rise, but a decline is probably real. So this is the number of papers on top and the derivative at the bottom in case the leveling off isn't clear. I'm searching for publications with topic including electrochemical impedance spectroscopy. Now, normalization is not trivial, but it's clear that the number is settling, if not decreasing. Potential reasons. Reason number one is the technique is becoming so mainstream that nobody lists it under topic anymore. Or trust in the AS data interpretation is starting to fade. And I believe the second is true. A lot of people are doing this test, but a lot of people are questioning the interpretation for good reason. And that reason being the fact that the analysis is ambiguous, and it's really the nature of the technique that makes the analysis ambiguous. You really have to do your work in disambiguation, if I borrow a word from Wikipedia. And I'd like to illustrate that ambiguity here. Now, remember, in impedance spectroscopy, the time scale of electrochemical processes is the only knob we have. We look at processes that are faster or slower than each other. But that can be done in multiple ways. So what I'm going to illustrate here is some data that I simulated based on the circuit model that I'm showing on the left. And the N, the capital N, is there to signify that this is the nested model. So I'm nesting one RC inside of another. Now, this is a standard two semicircle model, nothing too special, two time constants. And what I'm going to tell you now is that I don't have a single spectrum here. I actually have three spectra that are overlaid that can be calculated with all these different models. So the spectra of all of these three models, all with two time constants, for different R's and C's, all overlap. And this is analytical. This is not just coincidence. One can analytically show that the spectra for all three are identical. Now, the errors I'm showing are just the fits that I've done after I've done the simulation with one of them. But this is a problem. There is no way impedance spectroscopy can tell you whether your system behaves like the nested model, like the defective corrosion protective coatings do, or the void model on the very far right, like most fuel cells do. So you have to do your homework in addition to taking impedance spectroscopy in order to identify which model to use, and further, whether the R1C1 or R2C2 belongs to the anode or the cathode or vice versa, because the impedance spectrum will not tell you which is which. It will only tell you that there's a process that's fast, there's another process that's slow, and it'll tell you the parameters of the two, provided you know which model to use. So what I'm going to talk about for the rest of my Act 1 is three ways in my group we are trying to do this disambiguation. Number one is the use of temperature. We can look at temperature dependence of impedance spectra. And the temperature dependence clearly helps us identify which data feature belongs to which electrochemical process, whether it's activated, whether it's transport, kinetics, what the activation energies are, and we can back that and we can correlate that with other experiments in order to match features in the data to electrochemical processes inside the batteries. Number two is nonlinearity. This is an issue that everybody tries to avoid. We want linear spectra, but the system underneath is inherently nonlinear. Equations for kinetics and transport are always nonlinear. We just zoom in to keep them linear, or pseudo-linear, if you like that term. However, the degree of nonlinearity has information in it, and we are using that to identify processes as well. And lastly, I will show you some of our initial efforts to use time-dependent linear and nonlinear impedance spectra in order to use impedance spectra to directly fit fundamental properties of batteries. So let's get started with temperature dependence. Now, clearly, I am not the first one to think about changing the temperature of a battery while doing impedance. This is the first paper that I had seen back when I was working for Gamry. This was the EIS meeting in 2013 in Okinawa. I listened to a talk by Professor Moma where they showed that they varied the temperature of the cell, took the impedance spectrum, and measured the impedance spectra, and they used this to calculate activation energies for anodic and cathodic processes. They said the changes in capacitance were minimal, And the way they plotted it looks like it, but notice that these are logarithmic axes. So the SEI capacitance, for example, is clearly significant and not minimal, but I'll talk about that in a little bit. So here I'm showing two separate sets of data from two separate batteries. On top, I have lithium thionyl chloride battery. This is a battery that I've worked on quite a bit because it's fascinating. You can get 19 amp hours on a small lantern size battery, so D type for the Europeans. It is primary, so it's not rechargeable. It has a lithium metal anode. But the defense industry uses it quite a bit because 19 amp hours in D size is something that you cannot beat. The reason you can get that many amp hours, that much energy density, is because the solvent for the electrolyte, the SOCl2 on that figure, is also the cathode active material. That's what gets reduced. So you can see that the solvent and the cathode active material are the same, so it saves a lot of weight, and that's why you can get a lot of energy out of it. So you can see the spectra changes as expected. At low temperatures, the overall impedances are larger, both in the real and the imaginary side, and as temperature goes up, a lot of things change. So the very low frequency semicircle gets smaller super quickly, and then the high frequency semicircle stays about as it is as temperature goes up. Some middle frequency stuff come up, and at 35 degrees in particular, we start resolving two clear semicircles that used to look like one at lower temperatures. And we understand all of these, what's going on here. Here's another battery down here. This is lithium manganese oxide. This is the primary version, not the secondary version. This is non-rechargeable. And the thing that makes it non-rechargeable is the lithium metal anode. The rechargeable versions have lithium aluminum on the anode. And on the cathode now is a manganese oxide intercalation material. And you can see the impedance is clearly different. And further, the temperature dependence is different. So the argument I see in the literature every once in a while saying high frequency is one side, low frequency is the other, and this thing is SEI and the other thing is transport, I always question because there's no rule to memorize here. Every battery system is different. Further, every battery size is different. Further, every battery electrode coating thickness results in different behaviors. So there is really no good way to assign these without actually doing the work. This is not like infrared spectroscopy where you can say a peak at 1600 wave numbers belong to some CO double bond. Impedance spectroscopy requires understanding of these processes because timescale is the only knob we have, and it is not chemical specific. Okay, so we can take those resistances, plot them versus temperature, understand their behavior. Some of them behave exponentially, some of them behave linearly, and we can use that information to not only identify the proper process, but also understand that process, like getting activation energies or conductivity coefficients. One interesting point is the capacitances. So what you're seeing on the right-hand side of the slide are the two capacitances that we are identifying as the salt electrolyte interface. Now, in the thionyl chloride case, capacitance goes up as temperature goes up, and then it appears to go back down. And then in the manganese oxide case, it is more or less flat up until 45 degrees, maybe a slight decrease, but then it starts going back up. So the nature of the SEI and dielectric properties of the SEI are clearly different between these two, even though they are both lithium metal electrodes. And the change of that capacitance as a function of temperature is telling us something, We have been working on modeling this behavior, understanding this behavior, but we don't have anything beyond speculation up until now. So the capacitances have a lot of valuable information. We just don't know what those are up until now. Okay, so we do a lot of Arrhenius plotting here and extraction of activation energies, and how those change as a function of state of charge tells us a lot about what's going on with the electrode surface. And as this conclusion slide states, capacitances are super confusing. We understand the resistances, but capacitances are super confusing. We are working on modeling the behavior there. Okay. Let me talk about nonlinearity, because this is an issue that is near and dear to my heart, and it is valuable, although hard to do. Now, we are all familiar with issues like this, right? So the behavior of current and voltage, current versus voltage, in any electrochemical system is nonlinear due to its very nature. Anything that explains the kinetics, Butler-Volmer, Marcus, whatever other model you'd like to use, it's almost always exponential of some sort. Diffusion processes are explained by fixed laws, which are differential and nonlinear. So no matter what you do, your current voltage curve is going to be nonlinear. However, impedance requires a linear and stationary response. So you pull the standard trick of any scientist or engineer saying, if I zoom in to this graph long enough, if I go into a small enough point, it'll look like a line. Well, sure. But not every process is as linear as the other. So how linear a given feature in the data is might help us identify what that feature corresponds to. So on the impedance side, what this manifests itself as is harmonics. Okay, so if everything is linear, the signal on the voltage when you are applying a current is going to look like what you are seeing on the left-hand side at the bottom there. The only thing you see is the fundamental, and then the higher harmonics are all at the noise floor. This is logarithmic, so there's more than 2 orders of magnitude between these two. And then when you have something nonlinear, you have the fundamental, and then you have a lot of power in the second, third, fourth, fifth, and sixth. And how they order actually tells you something. And the fact that they exist tells you a lot of things in addition to how they are related with each other. Okay. Now, when we first started trying to do this, the instrumentation available, including our host Gamry, did not provide the nonlinear part of the signal to us. However, luckily, we could customize explain scripts, write out some Lissajous curves explicitly and manually ourselves, and do the Fourier transforms outside. However, currently, these things are available. So the harmonics and the total harmonic distortion are available through the software without any additional work. But now that I have my scripts doing additional work that I understand, I actually still am using my scripts. So when you collect the data and look at the Fourier transforms, you get things like this for every given signal. So at a given frequency, this is 100 hertz. There's not much nonlinearity in the higher harmonics. At 10 hertz, there's plenty. At 1 hertz, there's plenty for this particular signal. By the way, the modification to the scripts is in this paper. So you can see how I modified the explain code to do all of this nonlinearity work. Ultimately, you'll see plots like this. So what we are plotting here is the frequency of the excitation current. And then in blue, we are plotting the voltage of the signal at the frequency of the excitation. So if I'm applying the current at 1 hertz, blue at 1 hertz here corresponds to the voltage at 1 hertz. However, the green that's I'm plotting at 1 hertz actually corresponds to the power at 2 hertz, the voltage at 2 hertz. So for any given frequency, I have the fundamental and the harmonics plotted along the same vertical line. And we do this for the whole spectrum up to a kilohertz down to 100 millihertz. So when the system is linear and stationary, you can see that the higher harmonics are all less than 1%, actually mostly 5 parts per thousand of the fundamental. So this is just the noise floor of the measurement. When things are nonlinear and non-stationary, you can see the second harmonic is now super significant. The third is significant. The fourth is significant. Furthermore, there's actually a frequency dependence of this nonlinear behavior. So you can see the fourth harmonic is actually decreasing. Second is above third. We'll see cases where third is above second. Right here is the 5 hertz filter glitch that's switching in at 2.5 hertz. And when it switches in, there's a small glitch. So that's a filter glitch. Another one up here at 500 hertz due to the 1 kilohertz filter kicking in. Okay. Is this information useful? Well, before going into more details, I need to tell you a little bit about the initial transient. That's the middle panel. Now, this was an issue that my former boss, Max Yaffe, who's in the audience from Gamry, and I used to discuss when I was employed there. The point is, your current is coming in as 0, and then at some point you start turning on the sine wave. Right at the point that you're starting to turn on the sine wave, the system response is actually transient. The system was at equilibrium, and then it started all of a sudden. So the derivative at that point is actually undefined. And this is why there's also always a waiting period. And this waiting period is typically 1 cycle at the frequency you are measuring. And when you do that and calculate your impedance and your harmonics, unfortunately, what you get, hold on 1 second, I'll come back to this, is something like this. So this is the measurement result. You can see the fundamental on the left, the second harmonic on the right, third harmonic, fourth harmonic. And this is with a dummy cell, the 2 dummy cells that I'm showing up above. The 10 hertz and the 100 hertz are just the 2 dummy cells. So this was super confusing to us when we first measured it, because we are using linear components, right? We are using 2 resistors and a capacitor, which are linear. That should not give us a second harmonic and a third harmonic. However, it clearly was. So we decided to model this from first principles and look at the time domain differences of voltages on the resistances and the capacitances. So you can find the details on the paper whose reference is given on the left bottom. But ultimately what happens is the currents, and you can calculate this with nothing but Kirchhoff's laws, okay? It's actually physics 102 in Bilkent University. It's the freshman physics second half that you're taking. When the current goes through the capacitor, it is pretty steady. When the current goes through the resistor, it's pretty steady. It is right around this resonance frequency when the current is crossing over from one to the other, right this middle panel. You can see that actually the voltage is first dominated by the capacitor a little bit, and then it starts getting dominated by the resistance. You can see when it's dominated by the capacitor, it's more asymmetric. When it's dominated by the resistor, it's more symmetric. And in the middle, it is crossing over from one to the other. So this initial transient, even if you get rid of the first cycle, and this is the point I'm trying to make, even if you get rid of the first cycle, The second and the third and the fourth still have a transient response, which is exactly what we are seeing here. And what you're seeing at these low frequencies is just the instrument noise floor. This slide shows you that we can actually simulate this to the T. So the simulation results, the only thing this is missing is the noise floor. If I added the noise floor to this, this would look exactly like the next slide, which is measurement results. So lesson number one, if you want to measure the nonlinearity, beware that there will be effects from initial transients in the harmonics, especially with things like batteries who have high capacitances. It's really the capacitance that's giving you this issue, okay? Now that we know this, can we use that information? So here is a battery that is being measured under two conditions. On the left-hand side, you are seeing a DC0, AC 0.5. And on the right-hand side, you're seeing DC1, AC 0.5. Now, if you compare these two, the responses are pretty different. Let's start at the low frequency side. Remember, the green star is third harmonic, and the orange square, let's call it, is the second harmonic. So at low frequencies, you can see the third is above the second. And as we go to high frequency, we are getting second above the third. And under this condition, under a DC 1 milliamp, we always have second above the third. It turns out that when the harmonics are ordered like this, 2, 3, 4, 5, that's an indication of drift. And when you have 3 higher than 2, that's an indication of nonlinearity. So under this condition, our only issue is the battery voltage drifting. But under this condition at 0 DC, we have drift issues at higher frequencies, but we have clear nonlinearity issues at lower frequencies. And it turns out the low frequency in this particular battery, which is the lithium cyanide, is actually giving you information about a different process under 0 DC versus 1 milliamp DC. In 1 milliamp DC, it's really the cathodic process of thionyl chloride reduction. However, in 0 milliamps, it is the reaction that leads to the escape of SO2 that is happening on the cathodic side, because you're going between charge and discharge, which is something that you should not do on a non-rechargeable battery. So the nonlinearity here is actually telling me a lot of things about the process. Now, we've gone through this, and again, you can see the publication down below. We have done this for plenty of batteries, and we have made the assignments of different frequency regions, as you can see. And ultimately, I'll skip this slide in the interest of time. Ultimately, we can identify which processes based on nonlinearity for the various batteries. And we can actually modulate them a little bit with the DC current, like I've shown in the previous slide. Are we taking our own advice? Of course. You can see in the lithium manganese oxide case, when we plot the second harmonic, I'm talking about the bottom graphs here. The simulation is just the simulation of the initial transient, and you can see the nonlinearity we are seeing from the experiment pretty well matches the simulation. Now, there are differences because we are simulating with a capacitor and the battery exhibits a CPE. So that's really the difference between the two. And I didn't want to force my student to work out the Kirchhoff's laws for a constant phase element. So that's why I left it this way. However, for the thionyl chloride, there is, both in the second harmonic and more so in the third harmonic, an actual response that's above and beyond the initial transient caused harmonic, and that information is valuable. Okay, So once we understand the reasons for nonlinearity, and one of them being initial transient, we can now use that information to identify processes. Now, at this stage, I'd like to think more about what we have. We have temperature dependence of impedance that's helping us identifying a lot of parameters. We have the nonlinearity of impedance that's telling us a lot of things about which feature corresponds to what process. Now the question is, can we use all of that information and really go after fundamental parameters? Okay. Now, this thing actually started with, again, another talk. This was at the ECS meeting, I believe, in Seattle, since Matt Murbach was a student there under the supervision of Dan Schwartz. So what they did was they took a battery model, a model from Newman, Doyle-Fuller-Newman P2D type model, for those of you familiar with it, and they simulated spectra that are directly out of a fundamental model with all of these parameters that you see on the right. So capacitances, concentration of the electrolyte, diffusion constants, kinetics, self-exchange rate constants, transfer coefficients, conductivities, thicknesses, dielectric constants, whatever, okay? And then they said, I can simulate these impedance spectra, and whenever I collect my spectrum, I can match the spectrum with what I've calculated, and voila, I have my parameter set. The problem with this, as the table on the right shows, is it is degenerate. Multiple different parameter sets give rise to the same exact spectrum because, as I said, time constant is our only knob. If I flip the processes of anode and the cathode and give them the opposite time constants, I can get the exact same spectrum. And this can be very wild. For example, if I can attract your attention to this diffusion constant, which is the diffusion constant on the positive side, it can be -15 or -17. If I can attract your attention to this particular variable, which is an electric field, you can see it can go from -43 all the way down to -0.02. Here's another diffusion constant, -13, -19. So this can be very wild. So my idea was to use the temperature dependence and the nonlinearity in order to break this degeneracy. Now, luckily, I managed to convince a poor student to work on this. He is also in the audience. So what we are going to do is we are going to take this temperature dependence, we are going to take this nonlinearity, and we are going to fit the whole thing to fundamental models, okay? Now, in order to do this, we needed a battery model, and we did not want to write one of our own. So we decided to use PyBAM. For those of you unfamiliar with PyBAM, it is a battery simulation model based on a lot of different options, but typically either Doyle-Fuller-Newman porous electrode or single particle model. And it is open source, and they are actually quite active, and there will be a users meeting next year, I believe, in England for PyBAM. So, and hopefully we'll attend there as well. So we are using PyBAM as our battery digital twin. So this is how we calculate the impedance on first place. So we take our signal, we use our battery parameters, we use our temperatures, throw them into PyBAM. We calculate voltages at every frequency, at every temperature, and for every nonlinearity. And then we calculate the impedance. And then we compare experimental data with the impedance with an objective function to minimize, and we do the fit. Now, here are a list of parameters that we think we can identify. And this is listed with some sensitivities based on some paper from the Zauer group in Aachen, where they have looked at a lot of different DC type data. So this is not impedance, this sensitivity. This is charge, discharge, and cycle counts and states of charge and health. and the sensitivity of those to each individual parameter. So all of these are what we'd like to identify ultimately. So in order to do this, we are going to take the standard objective function that is used to do impedance fits, which is this one, which is looking at the calculated minus measured divided by measured with some weight for both the real and imaginary summed over frequencies. We are going to add another dimension to that, and that's going to be the temperature. So instead of fitting one spectrum at a time, we are going to fit 3 spectra at a time, as you can see in this animation below. But we are not going to stop there. We are going to go and add another dimension to this, and that's going to be the harmonics. And now we are going to have a 2D array. Now, this is not 3 by 3. This is actually 8 by 4, but that's much harder to visualize. So we've only visualized the subset here. So ultimately, we can do this to fit. Now, the name of the game here and the trick here is to use the correct model, find out the correct weights, and find a good surface for all the parameters. What we are battling with currently is that our processes depend a lot on where we start our parameters, because a lot of things are very multi-valued. So we need to identify the correct temperatures, the correct harmonics, and the correct weights in order to do the fits. And that is going to be the master's thesis of Eren Civan. Okay, so I've told you about the attempts that we do in order to disambiguate EIS analysis. And the 2 main additional pieces of information we have are still within impedance measurements, namely temperature dependence and nonlinearity. And hopefully we can combine all of that in order to get fundamental parameters. Let me quickly check my time. Ooh, okay. I've already gone past 35 minutes, so let me switch gears now to talk about noise. This is another topic that's near and dear to my heart as a former Gamry employee. And I'll first start by correcting the name. It's not noise, it's signal. One person's noise is another person's signal. And it's not something to throw away. Okay, now obviously we are not the first ones to think about doing noise. In corrosion world, noise has been measured since the 80s, and it's especially useful for things like pitting and crevicing. And since these things are stochastic, you need a stochastic way of measuring and understanding the details of the pitting and crevicing processes. One thing I'd like to emphasize here is the fact that the only way I can know that the data on the left-hand side is pitting and the data on the right-hand side is crevicing is by post-mortem analysis. I do not trust the math that can tell me, that can distinguish the two. So by post-mortem, I can actually go back and identify the types of signal saying this is pitting, this is crevicing. The figure on the right-hand side is actually obviously pitting and not crevicing. Okay. Now, for battery systems, the literature is a lot more scarce. The earliest paper, or one of the earliest papers we could find, was this one, where some electrical engineers looked for the battery with the lowest noise so that they could use for powering up amplifiers with low noise power sources. Unfortunately, what they are showing on the left-hand side is that the larger battery has a lower noise, and after working on this for 7 or 8 years, we know exactly why that is the case, so that's really not that exciting. On the chemical side, Pierre Roberge from Canada did some noise work on lead acids, and this is actually earlier than the paper on the left. This is 1989. But this was 1989, 10 to 12 with A to Ds. The only thing they could see was actually bubbles forming on the electrode surface, creating extra noise. Now, the way we are approaching this problem is the first thing we are doing is typically noise measurements are done in potentiostatic mode or zero resistance ammeter mode, which is a potentiostatic mode at a particular potential. Unfortunately, I do not like that. And the reason I don't like it is shown here. So this is a potentiostatic measurement that we are doing at 0 volts. And you can see that the current noise here, for example, this feature right here, right around 250 seconds, really overlaps a feature on the voltage. So since I'm trying to identify processes down inside the battery, I want my noise to be due to the battery and only due to the battery. And I do not want to have the question of, is this coming from some applied voltage noise being reflected on the current? So this could very easily be noise due to my electronics. This is well within the specs of the instrument. And that could be causing the current noise here. So when we are doing noise measurements in batteries, we don't apply anything. We just measure the voltage. So it's not only non-invasive, it's actually non-perturbing. We just listen to the voltage. However, the voltage measurement of microvolts on top of 4 volts is super tricky. The voltage reference that's used in order to suppress the background has noise of its own, and that can confuse the hell out of you. My first noise paper shows exactly the electrochemical noise of supercapacitors at different voltages, showing the effect of electronic noise of the voltage reference. So what we are doing in order to compensate this voltage is we are using another battery to compensate the first battery. So we keep them in parallel connection for a while so that they equilibrate to the same point down to the microvolt. And then we very quickly switch them to what we call anti-serial, which is a serial connection, but the poles are back to back. So the positives are facing each other. And this way, the DC potential between negative measurement and positive measurement is 0. And that way we can measure the voltage directly. And we have a little switch set up here that helps us go back and forth between the two super quickly. And that's what it looks like. And the red open wire here is one of the measurement ends, and this blue end is the other measurement end. And ultimately, we know how anti-aliasing works. That's what this right-hand side graph shows. And since all the signal is below 5 Hertz, we actually put the analog filter at 5 Hertz, and we measure things below 5 Hertz, and we are doing that correctly, as this figure shows. Okay. So we have done a lot of things. We have tried to identify the source of the noise of these batteries. As you're seeing on the right top, we've done a lot of materials analyses, XRDs, XRFs, infrareds. We've done a lot of things. We've looked at scanning electron micrographs, and none of them explained this difference. For lithium manganese oxide primary batteries, when we discharge them slowly, the noise is really at the background of our instrument. When we short them, and for these batteries, shorting just means milliamps of current. Shorting does mean 20 hours of current. They are pretty high resistance. You can see that the noise goes all the way up to almost a millivolt, and then goes back down a little bit. So this is 1 day shorted. It is measurable. 3 days shorted, this is huge. And then 7 days shorted, it goes back down. And the reason for this is, unsurprising in hindsight, is pitting corrosion. So when you discharge it slowly, as you can see, the metallic lithium actually dissolves, gets oxidized in a pretty uniform manner. So as the discharge level increases, it goes all the way down to the stainless steel current collector. When you short them, because it tries to do a lot of things at a very short time, the discharge starts happening where in the defects. And you can see that this looks a lot like pitting corrosion. It gets worse, And these are not scratches that we made when we were opening the battery, by the way. This is exactly how the battery discharged. And then when it comes to 7 days, we are almost back to the stainless steel bare bottom electrode. So this is the reason for that increased noise during discharge. Now, whenever we try to publish these things, this is actually fairly dated data. This is 2020. Whenever we try to publish this data, there is always a reviewer from the corrosion noise community that tells us, why aren't you using this particular mathematical tool? Everybody has their favorite mathematical tool, RQA, F-domain, wavelets, what have you. And there's always the attitude of, oh, do you not know how to do this? Well, the answer is we do. And we published a paper a couple of years ago showing why we don't like any of those and why we actually just want to look at the time domain without any external manipulations. Because whenever I start manipulating, I can get any and every result out of that data depending on what I want. Okay, so in order to illustrate this, I took this data, or we took this data that is 1 hour long, and we took 3 separate sections of it, and we started with a action that's deemed benign in the noise community, detrending. So just by detrending it, we can actually do a lot of damage, as you can see. The middle part looks like this is a trend, the red, it is going down. But as you look at the big picture, it's actually not going down. This is just a dip in time. And lower part and longer part seems not noisy. And if I try to go to these more advanced mathematical methods like RQA, all of these 4 are the exact same data. So I can pick whichever I want to publish. Here is the wavelets, very similar story. I can pick and choose whatever I want. There is a author that published quite a lot about noise. Most of them are single author papers. And his detrending in the paper is actually a 22nd order polynomial with triple moving average after that. So things like that make me really question the analysis, of course. So we are pretty adamant in just using the time domain data, doing everything we can experimentally to clean up the data with this anti-serial connection or whatever else we can think of, and trying to avoid the mathematical manipulations that are subjective as much as possible. One other experiment that clearly tells us this is the lithium metal and not anything else is this particular experiment right here. Now, I told you before that the lithium manganese oxide batteries that are rechargeable and non-rechargeable have only one difference between them, and that's the anode. One of them is lithium metal, the other one is lithium aluminum. So what you're seeing on the left-hand side, the red line is the noise we measure after a rechargeable battery is discharged. And the black line is the same on the non-rechargeable side. So the difference in the data is the difference in the interpretation. And I assure you that red line is not just a line that's drawn, that's actual measurement results. Now, what we have been struggling for the past few years, and we are pretty excited about this, but it's a hard experiment to do, is during charging. Because if you think about one of the bigger problems in batteries and electric vehicles is fast charge. The problem with fast charge is there are 2 competing reactions. One of them is intercalation of lithium, the other one is plating of lithium. And if it plates, you lose capacity. If it intercalates, everything is fine. We believe, and we have some pretty early indications in our preliminary testing, is that plating actually adds significant amount of noise, as you can see here, whereas intercalation does not generate noise. This is very hard to do reproducibly because we don't have a good set of batteries and conditions that reproducibly plates. And we typically want to measure at least 8 cells before we are sure that this is happening. So we think we find at least, well, we have some more prospects that we are working on right now. And once we can find a good reproducible way to plate lithium in commercial batteries that we can reproducibly measure, we will come up with a way of identifying lithium plating via electrochemical noise on the voltage. Okay, I'm not going to go on to concluding remarks since I'm already 6 minutes over time. I want to acknowledge the people who have done the work. So the guy with the eyeglasses on the very far right, this one in the back, he is doing the temperature-dependent nonlinear fitting. Dr. Katerji is now in Germany making electric airplanes, used to be in my group. He did a lot of the initial temperature-dependent EIS. Gözde is our noise master. She is the one who is doing all the noise work, and my son is messing all up. Okay, well, that's all I have. And thank you very much for bearing with me, even though I went over time.
Wow. Thank you, Burak. That was a very deep dive into, I think, what everybody is wondering about. You know, what more can you do with impedance and kind of these AC, well, applying AC signals, but also measuring kind of things in the AC or time domain. And so now let's take any questions. You can either message it, put it in chat to myself, the host, or a co-host, and we can get this started. So while everybody is kind of formulating their questions, I will ask one. You know, I was thinking about this serial and anti-serial kind of connection, and I saw the photos for the coin cells, you know, for people who maybe are working in larger form factors. Do you think there might be any challenges? You know,
Right.
and can
Thank
they
you very
use
much for
this
that question.
similar? Yeah. What's that?
Now,
Oh,
there are plenty of challenges. I'm actively trying to work on larger format cells. The problem is, as I mentioned when I was showing this data on the left, the larger the battery, the lower the noise. And this is simply due to physics 102 again. Voltage V is equal to Q over C. C, capacitance goes up as the electrode goes larger, and the voltage goes down. So the best we can do up until now, the best noise floor we've been able to get is things like this. So 2.5 microvolts. We need to do better than that. So Gamry instruments, you need to do better than that. So with larger format cells, noise will be lower. So if we can resolve nanovolts, that would be awesome.
so what you're
But
saying
I know
is
that's a challenge.
you're right. So you're either improving the instrument you're using, or maybe you are scaling down the battery while still maintaining its relevance to.
Yeah, I mean, in the electric vehicle industry, there actually the trend is going larger and larger. But I'm sure there will be, first of all, what I'm motivated by is the fundamentals behind this. Why is there noise? What is it telling me about the thing under the hood? But unfortunately, I don't get funded by that. So I have to hook into some application, and hopefully at some point I can find an application for a small cell here.
Right. But I mean, I think on some level, you know, finding partners would be very interesting for you, open new doors. Yeah. That's
true.
always the issue with the
That's right.
right with research. Okay, we have our first question. K Don asks, have you done any work measuring the noise using a reference electrode to separate the interfacial impedances, anode and cathode? And would you find that meaningful or not?
Okay, another great question. If I could have done it, it would have been very meaningful. The problem here is that notice I've only shown you noise data from commercial cells and nothing else. Over the years, we've tried to collaborate with people, trying to measure cells that are lab made. The problem is their reproducibility is horrendous. When we get commercial cells, the reproducibility is amazing. It's better than 0.5%, even for these coin cells that we are buying off the shelf from a supermarket. However, whenever I get a collaborator to make me 3 cells, I get 5 different results. Okay. So a lot of these, well, all of these cells with the reference electrode are handmade, not commercially made. And when we are measuring down at microvolt, we need reproducible results. We need reproducible cells. So if you can make these cells reproducibly with a reference electrode, I would love to collaborate with you.
All right, we have a second question. The user is asking about the plots for the first principle of fitting. And he or she pointed out that they kind of look like Tafel plots. And
well, they look weird, especially at the high frequency out here, simply because of the way the simulation worked. We had some numerical errors that we did not recognize at the time. Now we have fixed them. They look better these days, but I just didn't update my animation. So that's the weird part. And we are plotting Z real, Z imaginary, not mod and phase. So it looks kind of counterintuitive.
Right. I mean, that dip right there, what frequency is that?
This one?
Right.
That's the second harmonic. And that is, I do not know the significance of that frequency. I think I saw Eran's name in the audience. Maybe he can tell us if that dip has any significance.
Hocam, I believe it is due to for the numerical reasons, and I believe it is the 100 hertz, I believe.
Okay. No. They're talking about the dip. Jerome is asking about the dip right around, right below 1 hertz.
Right.
I don't know the reason.
Okay.
I mean, it's an order of magnitude, right? Roughly.
Oh yeah.
Dip,
Oh, yeah.
so it's very meaningful. It's almost
But it's
like
only
a
on the
resonance.
imaginary and not on the real. So we'll have to look into it deeper.
Very good. Are there any questions in the audience? I mean, you could raise your hand. Oh, here we go. Jayabrata Mighty. Sorry if I butchered that. And so the question is, I don't know, Burak, if you can also read it there.
Yep.
Or is it just directed to me? It's
I'm
just to me.
reading it. I can see this one.
Okay. Yeah, it's a question about getting passive impedance spectroscopy or using passive impedance. You might have to clarify on this.
Yeah, I'm not familiar with the term passive impedance spectroscopy.
It might just be referring to running it at the equilibrium potential or maybe the resting voltage, right?
Okay.
But I'm not sure.
Now, if you just have 1 hertz sampling frequency, the only impedance spectra you can get is much below 1 hertz. So I'm not sure I got this question.
Right. Well, we'll wait for a response. Is there any other questions? You can raise your hand and ask it directly if you'd like. All right. Anybody from the Gamry team interested in giving Burak a hard time?
I don't know about a hard time, but you commented about the larger cells not having as much signal. However, there were some of those tests that you drove the signal ended up higher when it was under load, I think, or during the charging phase. And it seems that's the time that you'd want to make that measurement. So if you've got if you can monitor that signal during a time where you have an increase in the signal that you're looking for, can you get larger cells? Can you get measurements off larger cells that way, even with when you can't get down into the nanovolt range?
It's It's nice that you asked that question because I was talking to Gözde about that experiment today. So we will certainly be looking at the noise during the charging phase. It's tricky because we want to charge them at high rates. So for an 18650 cell with 3 amp hour capacity, we want to be able to measure this voltage while it's under 9 amps. So we need to do a lot of controls on that, trying to make sure that the noise on the 9 amps is not what we are measuring. But that's exactly one of the experiments that we are after. And as I said, I talked to my student about that earlier today.
I mean, so there is a question, but I will follow up on this. Jacob's question is, when you have the larger form factors, there must be a thermal gradient as you're doing this, right? So does that really confound? Give me
Yeah,
a
so
hard time,
one of
Burak.
the nice things about being an academic is I can ignore thermal gradients that people on the field are working on, and I can put my cell in a thermostated box and get rid of that.
Really though?
There still could be something, but
Okay.
what I do is I put in my best effort to avoid it as much as possible, and then I say it's not there.
Yeah, fair point. Yeah. All right, we have a question from Schrader. What about lithium iodine primary batteries from pacemakers regarding reproducibility?
Okay, those we have not tested. However, we did test the zinc airs for cochlear implants, and those were pretty reproducible, but the zinc electrode was pretty quiet and not noisy. I did not think about lithium iodine pacemaker batteries, but thank you very much for the idea.
And
I'll take a look at that.
also, you can ask Litronic for future collaboration.
Yep, I saw that.
So there
I'll
you go.
certainly take a look at the company. I was not familiar with the company. By the way, my contact info was on my last slide. Feel free to write to me. Oops. Feel free to write to me and take a look at my website. The QR code does not go to anywhere else but the website. So feel free to scan the QR code as well. Feel free to write to me for questions or collaboration requests. I'm more than open. And all of these nice people in this picture would be very happy to collaborate with you as well.
All right. Last call for a last question. If not, let us please thank Professor Ülgüt for his very wonderful, very informative talk about impedance and noise, specifically of batteries. I think there's a lot to take away from this, especially considering the idea of the drift that we all understand, as well as this initial transient that I think less people really appreciate. So thank you. All right, so.
And I thank you for the opportunity and for all the attendees for attending.
All right, so I'm going to stop recording.